Watch a single coin flip in the air, and you are looking at pure chaotic uncertainty. Until that spinning piece of metal hits the ground, you have absolutely no way to know which side will face up. In probability, we call that single repeated action, the flip itself, a trial. What happens when it lands is the outcome. For a single trial like this, there are only two possible outcomes, heads or tails. If you just do this once, it is a completely random event. But if you take that exact same unpredictable action and repeat it, a distinct structure begins to form. Let's expand our experiment. Instead of tossing one coin, we toss three. Now we aren't observing individual flips, we are tracking how the outcomes group together. This table maps all results for 3 coins. Only one combination yields 0 heads. For exactly 1 head, there are 3 ways. 2 heads, also 3 ways. For 3 heads, we return to 1. The outcomes cluster in the middle. This visual highlights a mathematical connection. That specific counting sequence for our 3 coins, 1, 3, 3, 1, matches a row perfectly nested inside Pascal's triangle. The counting pattern is completely predictable. Let's push this scale to the extreme. Imagine dumping 100 coins onto a table all at once. What does the pattern look like now? If we tried to build a manual table for 100 coins, we would hit a massive computational wall. Every new coin doubles the number of possibilities. 100 coins produce 2 to the 100th power possible heads and tails sequences. That number is so large it defies human comprehension. We could never list them all. To understand a system of this size, we can't rely on brute force. We need a way to calculate the total number of possibilities without actually seeing every single one. Mathematics solves this with a tool called a combination. A combination allows us to calculate exactly how many ways a specific result can happen, completely bypassing the need to list out billions of sequences. If we want to find out how many ways we can get exactly 40 heads out of 100 coins, we use the formula 100 choose k, where k is the number of successes we're looking for. The math simply tallies every way to drop those 40 heads into 100 empty slots. This brings us to a common intuition trap. Since a coin has a 50-50 chance of landing heads, you might assume flipping a fair coin 100 times guarantees exactly 50 heads. When we run the combination formula, the reality is entirely different. The actual mathematical probability of getting exactly 50 heads is less than 8%. A fair coin does not enforce a perfect even split on every single attempt. What fairness actually does is dictate how variation balances out in the long run. This histogram maps the exact probability for every possible number of heads out of 100 coin tosses. As we can see, while 50 heads only happens about 8% of the time, the remaining 92% of the probability isn't scattered at random. Exactly 50 is still the highest peak on the board. It is the single most likely exact outcome, even if it happens less than 1 in 10 times. Look at the exact symmetry. Getting exactly 40 heads means you also got exactly 60 tails. Because the coin itself is fair, the probabilities perfectly mirror each other. You have the exact same mathematical chance of getting 40 heads as you do of getting 60. As you move further away from that 50-mark center point, the chances plummet. By the time you reach the far edges, like getting exactly 5 heads or 95, the odds are so microscopically small they are practically impossible in ordinary experience. This distinct, predictable curve resulting from repeated yes or no trials is called the binomial distribution. This curve proves that true randomness isn't flat or featureless. It has a precise, elegant architecture. What happens to the math if the system isn't perfectly balanced? Suppose we weight a coin so that it lands on heads 70% of the time. This image displays the general binomial formula. It accounts for uneven odds by introducing the variables n for the total number of trials and p for the probability of success on each individual trial. By setting that probability to 70%, the entire distribution physically shifts. The new bell curve remains symmetric, but it now centers perfectly around 70 heads instead of 50. The math holds up. Whether the odds are evenly split or heavily rigged, This formula allows mathematicians to accurately map the landscape of possible outcomes. This is a photograph of researchers running tests in a lab, and their work relies on the exact same logic. Whether you are tossing a metallic coin or testing how many patients out of 100 respond positively to a new medical treatment, you are counting binary outcomes across repeated trials. Run an experiment once, and you get an isolated, uncertain result. But run it thousands of times, and the variation begins to smooth out, revealing a clear, indisputable pattern. We often think of randomness as a complete absence of order, but the binomial distribution shows us that when you step back and look at enough data, chaos naturally organizes itself into perfect mathematical beauty.